All right, let's start with the second half of this, or not half, but last little bit here. Okay, determine the most stable. So we're looking at C2, 2 minus, B2, N2, 2 plus, and C2, 2 plus. We have our energy diagram here with our sigma 2s bonding orbital, our sigma 2s antibonding orbital. And then for everything to the left of O2, we're actually going to have our pi 2p bonding orbital coming next in energy, then our sigma 2p bonding, and then pi 2p antibonding, and lastly, sigma 2p antibonding. For carbon, C2, 2 minus, carbon has 4 valence electrons, so 2 of those would be 8, but we have a 2 negative charge, so that's going to make 10. So I've got to put in 10 electrons. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my bond order here should be 8 minus 2 divided by 2, or should be a bond order of 3. Now we'll do the same for boron, B2. Boron has 3 valence electrons. 2 of those will be 6. So 1, 2, 3, 4, 5, 6. So here I'm going to have 4 electrons in bonding orbitals, 2 in antibonding, and a bond order then of 1. Now, N2, 2 plus, nitrogen normally has 5 valence electrons. 5 plus 5 is 10, but we have a 2 plus charge, so we're going to have 2 less than that. So 8, 1, 2, 3, 4, 5, 6, 7, 8. So I've got 6 electrons in bonding orbitals, 2 in antibonding. So my bond order now is 2. And then lastly, we're going to do the C2, 2 plus. So 4 plus 4, 8, but 2 plus charge should give us 6. So 6 electrons, 1, 2, 3, 4, 5, 6. So 4 electrons in bonding orbitals, 2 in antibonding. Bond order is 1. So which one has the highest bond order? C2, 2 minus. Which one is going to be the most stable? C2, 2 minus. 19, a large balloon is initially filled with 15 liters of gas at a pressure of 2,575 millimeters of mercury. I want that in atmospheres, so I'm going to divide 2,575 by 760 and get 3.388 atmospheres, which is equal to N times our ideal gas constant, times our temperature, 353. So this would allow me to find the number of moles of gas that we're dealing with, which in this case should be 1.75 moles. Then the balloon goes under differing conditions. So now we're trying to solve for the volume. We know the pressure, 1.45 atmospheres. We know the number of moles, the ideal gas constant, and we're solving for the volume. You could also do, was it PV over T1 equals PV over T2. And there we go. Our volume is 25.1 liters. 20, what mass of SO2 is contained in a 13-liter tank at 3.58 atmospheres. We're trying to find the number of moles of the gas. Once we know that, we can find the mass. We know the temperature. So N should be 1.473 moles. Now that is that many moles of SO2 gas. So if we multiply that by the molar mass of SO2, we'll get the mass in grams for that volume of gas at that pressure and temperature. And lastly, what's the volume of gas if we have 11.2 grams of O2 at 7.78 atmospheres at 415 Kelvin. So I need to know N, so we can solve for then our only variable V, the volume. So I have to divide the mass of O2 by its molar mass to find out how many moles that is. And it is 0.35. So now what we're trying to do is find the volume. So if I rearrange PV equals nRT to just trying to find the volume, I have nRT over P. We know our N. Here's our ideal gas constant. And our temperature, all divided by our pressure. And if I solve for that, we should see that the volume is 1.53 liters. All right, that's everything. If you have any questions, please reach out to me. I will have normal office hours next week. If you think there was an issue with the Scantron, please stop by my office. We can pull the Scantron and double check it. Otherwise, I will see you all Monday.